So let's go over the acids and bases part C in class activity. So this is just again showing you the concept map that we use that helps show the relationship between pH, pOH, and the H plus and the hydroxide ion concentration. And when we need to relate the H plus concentration, the hydroxide concentration, so the product of those two is 1 times 10 to the minus 14th, and this is also the kW of water. So Ka times Kb equals the kW of water, because sometimes you're given the Ka, but you need the Kb for calculations, or you may be given the Kb, you need to calculate the Ka. So this relationship shows you how to interchange between the two. Okay, this is another concept map that I want to show you and why it's so important to be able to look at a compound and be able to figure out whether it's ionic or molecular, and if it's an acid or a base. So that's one of the skills that you should have from Chem 1A. So if it's ionic, so if it's a salt, so a metal and a non-metal, then we need to determine if that salt is acidic or not. So if it's acidic, we treat it like a weak acid. If it's neutral, no calculations needed, it's just a pH of 7. If it's basic, we treat it just like a base. And notice how similar these are to each other. Whereas the acid form, we've got the Ka. So the acid dissociating is the H plus in the anion, or the base, where the base takes a proton from water to make the conjugate acid and the OH. But still, the constants are products over reactants. Now, if it's acid, we need to figure out whether it's strong or weak. If it's strong, it completely dissociates. And so the negative log of the concentration of the acid will give you this pH. And if it's weak, it's going to work just like the weak acids over here. And then if it's base, if it's a strong base, excuse me, make sure you balance the equation so that you have, the ratio of the metal to the hydroxides, and you take into account the hydroxide concentration for the ratio that are there. And if you want to do the pOH is the negative log of the OH concentration, and then 14 minus the pOH gives you the pH. And then the weak works just like we did for the weak base over here. So the base plus the water makes the conjugate acid and the hydroxide. And the Kb is associated with that base reaction, and it's still products over reactants. Now, if you like this concept map, this is available to you as part of the PowerPoints in our module for acids and bases on Canvas. Now, the relationship of Ka to Kb, the Ka of an acid to Kb, the conjugate base. We talked about that a little bit on the concept map, but remember here we have a reaction for an acid. So acid going the forward direction to make its conjugate base. And so the Ka is products over reactants. So this is the K for the acid form. And if we write this reaction going in the other direction, so that conjugate base, the conjugate base reacting with water makes HA and OH. So this would be the Kb. So it's still the products over the reactants. And remember, when we add equations, we multiply the equilibrium constant. So I'm adding these two equations. These A minuses cancel out and the Ha's cancel out. So that we're left with two waters, H3O, the hydronium, and the hydroxide. So the Ka times the Kb, so this Ka times Kb, notice the Ha's cancel out, the A minus cancels out. So we're left with the hydronium times the OH concentration. So that's where we're getting the Kw equals the Ka times Kb. Because also notice too that if we were to write the equilibrium constant for this reaction, products over reactants, the hydronium concentration times the concentration of the hydroxide but the water is pure, so it doesn't show up in the equation. Okay, so there's a little background on the theory. Let's look at question 1. Determine the pH of a 0.235 molar sodium hydroxide. So we should be able to look at this and know that that sodium hydroxide is a strong base and it completely dissociates into water. So the sodium hydroxide, there's our reaction as it completely dissociates. The concentration of the sodium hydroxide, once it dissociates, will be the new concentration of the hydroxide. So negative log of that concentration. And so the pOH equals that 0.469. Sorry, equals that 0.429. So if we round it to 2 sig figs, the 0.63. Now in part 2, this is another strong base, but this time there's 2 equivalents of hydroxide for 1 base. So we may have to make sure we take that into consideration. So when that starts to dissociate, barium hydroxide breaks up into barium 2+ and then 2 hydroxides. So the initial concentration of that barium hydroxide is 0.116. All of this is going to be dissociated. So this is a one-way reaction. So we take all of this. And so minus 0.116, because it's 1 equivalent of this. We're going to make 1 equivalent of the barium 2+, but we're going to make 2 equivalents of the hydroxide. So that's why we have to multiply that hydroxide concentration by 2. So our concentration is 2 times the 0.116, which is the 0.232. If we take the negative log of that, that gives us the pOH. And if we put that on a calculator, it's 0.63. And if we want the pH, 14 minus the pOH, and that's how we're getting 13.365. So we're getting C for the answer there. Now in 3, they want to know which of the following will form an acidic solution in water. So we need to look at the salts, because this is a salt, this is a salt. These are all salts because we have the polyatomic cation and the anion, metal and nonmetal, metal and nonmetal, metal and nonmetal. So these are all ionic compounds. So these are all ionic, but some may be acidic or neutral or basic. So when we look at this, we look at the ammonium chloride. The ammonium is the conjugate base of ammonia. Sorry, it's the conjugate acid of ammonia. So this will be acidic when we put it in water. The chlorine, we can think of this as coming from HCl, and that's a strong acid, so that produces a neutral. But the NH4 comes from NH3, so that's a weak base, and this is a weak acid. So if we look at the others, so lithium is an alkali metal, so that's neutral. The iodine, also think of that coming from HI, that's a strong acid, that's also going to be neutral. Potassium, think of that from potassium hydroxide, that's strong, so that's going to be neutral. HNO3 is a strong acid, so that produces a neutral salt. Salt is going to be neutral. But the sodium fluoride, for the sodium, think of this coming from sodium hydroxide, strong base, so neutral sodium. But the fluoride, think of that coming from HF. HF is a weak acid, and so the F minus would be a weak base. So this would produce a basic solution if we were to dissolve this in water. So that's the analysis that we need to do. So of these, it's the NH4Cl that's going to produce the acidic solution when dissolved in water. So just kind of going over some of those rules for classifying the salts as acidic, basic, or neutral. So if the salt cation is the counterion of a strong base, and the anion is the conjugate base of a strong acid, it'll form a neutral solution. So think about sodium chloride coming from sodium hydroxide and the Cl from HCl, calcium hydroxide and nitric acid produce this neutral calcium nitrate salt. So these are all neutral examples. So if you were to put these in water, the pH would be 7. If the salt has a counterion of a strong base, so the anion and the anion is the conjugate base of a weak acid, then it's going to form a basic solution, because a strong base produces the neutral, but the weak acid produces the weak base. So if we look at this here, the sodium part is going to be neutral, but the fluorine coming from HF is a weak acid, F minus is the conjugate base, that's a weak base. So it's going to be basic in solution. Same thing here with this NO2. So this is from nitrous acid. So the nitrite ion here is going to form a basic solution. If the salt is the conjugate acid of a weak base and the anion is that of a strong acid, we get acidic. So the chlorine here coming from HCl, so that part's neutral, but the NH4, like we saw in the previous problem, so that's coming from a weak base, so this part is going to be acidic. And if the salt cation is a highly charged metal ion and the ion is the conjugate base of a strong acid, it will form an acidic solution. So even though the nitrate here, so nitrate coming from nitric acid, that would produce a neutral form. The aluminum is super high charge, that aluminum 3+, that aluminum 3+ is going to want to interact strongly with the hydroxides in water. And so it will make it leave behind the H+. So that's how we get an acidic solution. Now, if the salt cation is the conjugate acid of a weak base and the anion is the weak base, the pH of the solution depends on the relative strengths of the acid and base. You have to compare those Kas and Kbs. Now in question 4, they want us to determine the Kb for cyanide ion, and they give us the Ka for hydrogen cyanide. So they give us the Ka and we want the Kb. And we have to remember that Ka times Kb equals Kw, and Kw is a constant. So Kw divided by the Ka will give us the Kb. So Kw is 1 times 10 to the minus 14th. They told us that the Ka is 4.9 times 10 to the minus 10. So this is how we're getting a Kb of 2.04 times 10 to the minus 5. So this is how we're getting D for this problem. Now in 5, they want us to determine the pH, and they've given us the concentration of an ammonia solution, and they give us the Kb of the ammonia. So we need to write what's going on in this reaction. Because remember that ammonia, when you put it in water, the ammonia is going to take one of the protons from the water to make the ammonium, and that's going to leave behind the hydroxide ion. So if you're in lab and they tell you to get a certain concentration of ammonia solution, it may be labeled as ammonium hydroxide, because part of the ammonia that's in there will actually be existing as dissociated ions, ammonium hydroxide. So this is the equation, the NH3 with the water, so it makes the ammonium and the hydroxide. So I'm starting with my Rice table, so my reaction. Initially I have 0.188 molar of the NH3. So we've got 0 of the NH4 and the 0 of the hydroxide. I just didn't show them here. And since this is a weak base, we lose some, so minus X, plus X, plus X. And then we're going to set up our K, so products over reactants. So X squared over the 0.188 minus X, we can use the approximation. So multiply these two by each other and take the square root to find X. So this X represents the hydroxide concentration. So now that I've got the hydroxide concentration, I can take the negative log of that, and that gives me the POH. And then 14 minus the POH gives me the pH is what we're looking for. So that's that 11.26. So that's how we're getting B for this problem. Now in 5, they're asking us to determine the pH of a 0.22 molar sodium fluoride solution, and they give us the Ka of HF. So remember that sodium fluoride will actually form a basic solution. So the fluoride, when we put it into water, the sodium is going to completely dissociate, the salt will, but the F minus, this is the conjugate base of the weak acid HF. So F minus, when it base, when it reacts with water, we protonate it to form the conjugate acid, and that leaves behind the OH, so the hydroxide. And the concentration of the fluoride ion is 0.22 molar. So this is a weak base, and it's dissociating. So we're minus X, plus X, and plus X. We're going to set up the K, but the K that we have is the acid, but we're working with the base form of the reaction. So I need to convert my Ka to Kb. So remember, Ka times Kb equals Kw. So if I divide the Kw by the Ka, this is how I'm getting the Kb. And so we said the X, so we solve for X here, the hydroxide concentration, take the negative log of that. And so the negative log of that is the POH, 14 minus the POH equals 8.90. So again, we just took our equilibrium constant expression, our products over our reactants, set it equal to the Kb because we're working with a base. That's where I'm putting this K value from. So that X represents the hydroxide concentration. We took the negative log of that to give the POH, and then 14 minus the POH gives me the pH.